Hey everyone, I am Ghada Almashaqbeh from UConn. In this talk, I will tell you about supporting privacy for payments as well as arbitrary computations on blockchains. I will tell you why this is challenging and where we stand with respect to the current and potential solutions that we have. Imagine a world where we can use Bitcoin to pay for everything. So we have the blockchain, which is simply a public immutable log of all the transactions that happened so far in the system. This blockchain is maintained by the miners, each of which is holding a full copy of this log and working on extending it. Let's take video on demand as an example. In order to pay for a video, the user's wallet will issue a transaction to transfer coins from the user's address to the vendor's address, and it will broadcast this transaction to the network. The miners will validate all transactions they receive, and they will package them in blocks. And then they will compete with each other to solve a mining puzzle. Only the winner will get to append the new block to the blockchain. At that time, the transaction will be published on the blockchain, and then the user, the vendor, and everyone else will be able to see it, which implies that the payment has been received. This model, unfortunately, suffers from two main limitations. The first one is functionality related. Bitcoin is mainly about currency transfer, and it has a limited scripting language. So it doesn't allow the users to ask the miners to execute arbitrary code, and it doesn't allow them to build sophisticated applications on top of its blockchain. The second limitation is about privacy. So remember, the blockchain is public and anyone can read its content. So yes, we use random looking Bitcoin addresses that don't require real identities. And yes, we can be extra careful and generate a new address for each new transaction. However, all these techniques support only pseudo-anonymity. Several studies have showed that transaction linkability can be utilized to link these addresses back to their real owners. So back to our example, everyone will be able to tell that this user has purchased a video from this specific website or a specific vendor. Addressing these two limitations started almost in parallel, and initial solutions went different directions. In other words, they either improved the privacy of the Bitcoin model, or they extended its functionality but remained public. Let's explore both directions, starting with the functionality one, and see if we can achieve both of them at the same time. Ethereum was born to address the functionality or the limited functionality of Bitcoin by allowing the users to execute arbitrary code on its blockchain, and it pioneered this movement. Naturally, other systems inspired by the Ethereum model have emerged, such as Algorand and Cardano. In this model, the miners form a global virtual computer. Users can write arbitrary programs and deploy them on the blockchain as smart contracts. Anyone can ask the miners to execute any function in these contracts. So a user, when invoking a function, will provide inputs. The miners will perform the computation over these inputs and produce outputs, and then update the blockchain state accordingly based on these outputs. This builds a model for computing on demand. It's powerful, and it found numerous applications such as decentralized governance and decentralized finance, or DeFi, and many others. On the privacy side, initial solutions targeted the Bitcoin model with the goal of mainly supporting private payments. This resulted in several academic and industrial initiatives such as Zcash, Quiz, Monero, and many others. And the general paradigm behind these solutions is hide and prove. So instead of sending a transaction in the clear to the network, hide it inside a cryptographic commitment or simply encrypted. And to allow validating this transaction to make sure that it is correct without revealing its content, generate zero-knowledge proofs attesting that the hidden transaction satisfies the correctness requirements as stated by the system. So again, back to our example, a transaction will be translated into two components. First, the user's wallet will encrypt the transaction, and then it will generate a proof. This proof simply states that the user's or the user's transaction, which is the hidden transaction, satisfies the correctness requirements that miners usually check. At a basic level, these include that or attesting to the fact that the user owns the coins that she or he wants to spend, and they are not spending more currency than what they own. This proof is publicly verifiable, so the miners and anyone will be able to verify that the hidden transaction is correct. In this paradigm, anonymity is achieved using what is called anonymity sets. So the zero-knowledge proof will also attest to the fact that among a set of private coin addresses, the user owns one of them without revealing the address itself. But remember, Bitcoin is still public. Applying core changes like these that we just described to the network protocol will result in a hard fork if not all the miners accept the changes. Such hard forks will result in two or more blockchains, and it partitions the network and the mining power. For this reason, private or privacy-preserving payment solutions produced new systems with their own blockchains and native currency rather than being updates to the Bitcoin network protocol. So we have systems that improve the functionality of Bitcoin, such as Ethereum. And we have systems that improved the privacy of Bitcoin, such as Zcash. And the question is, can we have it all? In other words, can we have privacy-preserving smart contracts that operate on private inputs and produce private outputs? More initiatives have emerged towards addressing this question, such as Zether, Zexi, Smartofacci, Kachina, and many more. The solutions or these solutions adopted two paradigms, the off-chain and on-chain. The off-chain paradigm, kind of like which paradigm they used, it depends on where the private computation is being performed. In the off-chain paradigm, the users or maybe other parties will perform the computation off-chain, meaning locally, while in the on-chain paradigm, the computation is performed by the miners themselves on the blockchain. In more details, the off-chain approach performs the computation over the actual inputs locally. Then it encrypts the inputs and the outputs and provides zero-knowledge proofs that the computation has been done correctly. Several systems have adopted this approach, such as ZK and Zexi, to name a few. So The users or the end users themselves perform the computation over their inputs. Then the users also encrypt the inputs and the outputs and generate zero knowledge proofs, while the miner's only role is just to verify the zero knowledge proofs and apply any state changes to the blockchain resulting from the computation, such as transferring currency, for example. So most of the heavy lifting work is done on the user side, and we no longer have the computation on demand model. So now the users themselves, they have to coordinate and perform the computation rather than asking the miners to do that for them. I should note that there are other off-chain solutions where they let the users delegate the computation to a trusted third party or trusted hardware instead of having the users do them. But I'm not going to discuss these in this talk. On the other hand, the on-chain private computing paradigm extends the paradigm of private payments that we saw before. In the sense that we don't only hide or encrypt the inputs and provide proofs that they are correct, we also let the miners perform computations over these encrypted inputs and produce encrypted outputs. Smart SHE introduced this idea where it combines fully homomorphic encryption and zero knowledge proofs to build a privacy-preserving smart contract scheme. In particular, fully homomorphic encryption allows us to compute or operate over encrypted inputs. So we have two operations, homomorphic add and homomorphic multiply, that allows us to add or multiply the ciphertext of inputs and get a ciphertext of the actual results, which is the actual sum or the actual multiplication. Having these two basic operations allows us to compile any computation into a privacy-preserving format using these operations. And again, we still need the zero knowledge proofs to attest or to provide proofs that the encrypted inputs are correct and valid. Using these operations, a smart contract can be compiled into a privacy-preserving format or version by involving homomorphic add and multiply instead of the regular ones. Users can invoke any function in these smart contracts, and they provide encrypted inputs, zero knowledge proofs for them, and then the miners will execute the computation over these encrypted inputs and provide encrypted outputs. These outputs can be only decrypted by the key owners under which the inputs or the original inputs were encrypted. So only those users will be able to decrypt the results. This builds a model for private computing on demand, because as you see, the heavy lifting work of the computation is done on the miner's side, and users can simply just submit requests to have the computation being performed for them. So is the problem solved and it is just a matter of selecting a solution flavor? Unfortunately, no. Private computation over blockchains introduce several challenges that need to be addressed before having any viable solution. Concurrency is a huge problem when dealing with accounts. Changing the state of an account will invalidate all pending zero knowledge proofs tied to the original state of that account. And this, in turn, will invalidate all transactions tied to these proofs. The current solutions that we have rely on locking these accounts and delaying any currency deposits until all pending zero knowledge proofs are verified. But of course, this creates an availability and usability problem in the system. Another issue is dealing with inputs belonging to multiple users. So for the on-chain model, this means that we have inputs encrypted under several public keys. An idea here is to use multi-key fully homomorphic encryption schemes that allows us to perform computation over inputs encrypted under different keys. However, the decryption process for these schemes is interactive and requires all users to get together in order to decrypt the results. For the off-chain paradigm, it's like operating on inputs belonging to multiple users increases the burden on the end user themselves, because these users, they have to get together and coordinate the computation over their private inputs using, for example, multi-party computation protocols, and produce the output. And these protocols are usually interactive and computationally heavy. Efficiency also is a big problem. Privacy-preserving solutions for blockchains usually rely on advanced cryptographic primitives that incur high computation and storage costs. For example, generating a zero-knowledge proof to attest to the correctness of even a simple computation can take the user more than a minute, while this takes only a few milliseconds for a private payment. On the storage side, a single homomorphic multiplication operation can generate a ciphertext of a size exceeding 100 kilobytes. And this is compared to just less than 1 kilobyte, which is the size of a private payment. This adds to the efficiency problems that permissionless public blockchains already have and trying to solve. In my opinion, the path forward doesn't necessarily mean that we have to be on one edge of the spectrum. I think having a hybrid solution is better in the sense that we reduce the amount of computation to the minimum, or which is the on-chain computation, to the minimum level required for coordination, while doing the rest of the work off-chain, perhaps on a secondary temporary chain managed by a subset of the miners, for example. And of course, optimizing for efficiency is a key, such as developing more efficient fully homomorphic encryption and zero-knowledge proof systems. These will also promote the privacy-preserving applications and techniques when applied to blockchains. So, bottom line, privacy is critical for the future of blockchain systems, especially those employing or supporting smart contracts. And yes, lots of work has been done, but this is just the beginning. More efforts are still needed on both the research and the engineering sides to address the challenges that we still have. Thank you so much for listening, and I hope that you found this talk useful. Thank you.